Climate change and the built environment. Table of content. Prologue. Chapter 1, Introduction to Climate Change. Chapter 2, Science of Climate Change. Chapter 3, Impacts on Society and Infrastructure. Chapter 4, Overview of the Built Environment. Chapter 5, Energy Consumption in Buildings. Chapter 6, Transportation and Urban Form. Chapter 7, Designing for Resilience. Chapter 8, Sustainable Materials and Construction. Chapter 9, Policy and Governance. Chapter 10, Mitigation Strategies for the Built Environment. Chapter 11, Financing Climate Resilient and Low-Carbon Infrastructure. Chapter 12, Monitoring, Evaluation and Reporting for Sustainable Built Environments. Chapter 13, Community Engagement and Behavior Change. Chapter 14, Technology and Innovation in Climate Resilient Cities. Chapter 15, Future Trends and the Path to Net Zero Cities. Chapter 16, Conclusion and Recommendations. Prologue. In the early decades of the 21st century, humanity stands at a critical juncture. Cities, home to more than half of the world's population, are both engines of economic growth and epicenters of environmental impact. Concrete, steel, and glass dominate skylines, powering progress but also fueling greenhouse gas emissions that drive climate change. Every street, building, and public space is implicated in this unfolding story, and the decisions we make today will define the resilience, sustainability, and livability of cities for generations to come. The built environment is not merely a backdrop for human activity, it is an active participant in the climate narrative. Buildings consume vast amounts of energy, transport networks channel emissions across cities, and urban infrastructure shapes the flow of water, heat, and air. Yet embedded within these same systems lies the potential for transformation. The design of a building, the planning of a neighborhood, the materials chosen for construction, all these decisions carry the power to reduce carbon footprints, protect communities, and foster adaptation to a changing climate. This book explores the intersection of climate change and the built environment. It examines how urban systems contribute to global warming, the risks cities face from extreme weather events, and the strategies that can mitigate environmental impact while enhancing resilience. From energy-efficient buildings and low-carbon materials to smart technologies and community engagement, the chapters ahead illuminate the tools, policies, and innovations reshaping our cities. But this is not a story of technology alone. It is a story of people, planners, architects, policymakers, investors, and residents, whose actions, behaviors, and decisions ultimately determine whether cities evolve into climate-resilient havens or remain vulnerable to environmental upheaval. By integrating science, policy, finance, and human-centered design, the built environment can transition from a source of emissions to a solution for sustainability. Climate Change and the Built Environment invites readers to envision this transformation. It challenges conventional thinking, presents evidence-based strategies, and highlights real-world examples of cities and communities pioneering the path to low-carbon, resilient futures. Above all, it underscores a fundamental truth. The choices we make in designing and managing our cities today will echo for decades, shaping not only the skyline but the very climate we inhabit. This book is a guide, a reference, and a call to action. For in the architecture of our cities lies both the challenge of climate change and the promise of its solution. Chapter 1, Introduction to Climate Change. Understanding climate change. Climate change refers to long-term alterations in temperature, precipitation patterns, wind, and other elements of the Earth's climate system. Unlike short-term weather variations, which can change daily or seasonally, climate change represents persistent shifts occurring over decades, centuries, or longer. The Earth's climate has always been dynamic. Ice ages, interglacial periods, and volcanic events have historically caused significant changes. However, the term climate change today primarily refers to the accelerated changes caused by human activities, especially the burning of fossil fuels, deforestation, and industrialization, which have increased atmospheric concentrations of greenhouse gases. The scientific consensus is clear: the global climate is warming, and human activity is the dominant factor driving this trend. According to the Intergovernmental Panel on Climate Change, IPCC, the average global surface temperature has risen by approximately 1.1 degrees Celsius since the pre-industrial period, 1850 to 1900, with profound consequences for natural and human systems. Historical perspective. Climate variability is not a new phenomenon. Paleoclimatology, the study of ancient climates, shows that Earth has undergone multiple warming and cooling cycles over millions of years. For instance, ice ages, extensive glaciations covered large parts of the northern hemisphere, dramatically affecting global ecosystems. Medieval warm period, ca. 950–1250 AD. Some regions experienced elevated temperatures, which impacted agriculture, population distribution, and urban settlements. Little Ice Age, ca. 1300 to 1850 AD, a period of cooling that caused shortened growing seasons, crop failures, and social stress in Europe and North America. While these events were driven primarily by natural factors, solar radiation fluctuations, volcanic activity, and ocean circulation changes, the rapid warming observed since the Industrial Revolution is unprecedented in the geological record. Fossil fuel combustion, industrial agriculture, and urban expansion have amplified the greenhouse effect, trapping more heat in the atmosphere than at any time in at least 800,000 years. Key drivers of modern climate change. The current phase of climate change is primarily anthropogenic. The main drivers include greenhouse gas emissions. Carbon dioxide, produced by burning fossil fuels, cement production, and deforestation. Methane, carbon tetrahydride, emitted from agriculture, especially livestock, landfills, and natural gas systems. Nitrous oxide, dinitrogen monoxide, released from fertilizers, industrial processes, and combustion. Fluorinated gases, synthetic gases used in refrigeration and industrial applications with high warming potential. Land use change. Urbanization, deforestation, and industrial agriculture reduce carbon sequestration and increase heat retention. Industrial and transportation activities. Cities, factories, and vehicles contribute significantly to energy consumption and air pollution. These factors interact with natural processes, creating feedback loops that accelerate warming. For example, melting polar ice reduces the Earth's albedo, reflectivity, causing more solar energy to be absorbed and further warming the planet. Observed impacts on the environment. Climate change manifests in multiple environmental changes, including rising global temperatures. Average surface temperatures are increasing, affecting ecosystems, agriculture, and human health. Extreme weather events, increased frequency and intensity of hurricanes, floods, droughts, and heat waves. Glacial retreat and sea level rise. Melting glaciers and thermal expansion of seawater contribute to coastal flooding and habitat loss. Ocean acidification. Increased carbon dioxide is absorbed by oceans, affecting marine life and fisheries. These environmental changes also influence the built environment. Infrastructure not designed for new climate extremes may fail, urban areas may become hotter, and coastal developments may face chronic flooding. Understanding these dynamics is essential for architects, planners, and engineers aiming to create resilient and sustainable built environments. Climate change and human society. The impacts of climate change are deeply intertwined with human society. Health risks, heat waves, vector-borne diseases, and poor air quality affect vulnerable populations. Economic implications, damaged infrastructure, lost productivity, and disrupted supply chains create significant economic burdens. Social inequality. marginalized communities often face disproportionate exposure to climate hazards, especially in urban areas with inadequate housing or flood protection. Recognizing climate change as both an environmental and social challenge is crucial. The built environment is not just a passive backdrop, it can amplify or mitigate these impacts. Cities, buildings, and infrastructure can either exacerbate vulnerability or serve as tools for adaptation and resilience. Scope of the book. This book explores the intersection of climate change and the built environment, examining how climate change affects urban areas, buildings, and infrastructure, strategies for mitigation, reducing emissions, and adaptation, building resilience, innovative design, planning, and construction practices that respond to a warming world. By integrating scientific understanding, engineering principles, and urban planning strategies, this book aims to equip professionals with the knowledge needed to create climate-resilient cities and sustainable buildings. References for Chapter 1. IPCC 2021, Climate Change 2021, The Physical Science Basis. Cambridge University Press. NASA 2022, Global Climate Change, Vital Signs of the Planet. National Research Council 2010, Adapting to the Impacts of Climate Change. Pachori, R.K. and Mayer, L., eds. 2014 Climate Change 2014 Synthesis Report. IPCC. Chapter 2, Science of Climate Change. Introduction. Understanding the science of climate change is crucial for architects, engineers, urban planners, and policymakers. Climate change is not just a conceptual issue, it is a physical process governed by atmospheric chemistry, energy flows, and complex feedback mechanisms. This chapter examines the fundamental scientific principles, the role of greenhouse gases, climate models, and the observed environmental changes that directly influence the built environment. The greenhouse effect. The greenhouse effect is the primary mechanism driving contemporary climate change. It is a natural process that keeps Earth's surface warm enough to support life. Incoming solar radiation. The sun emits shortwave radiation that passes through the atmosphere and warms the Earth's surface. Outgoing infrared radiation. The Earth emits long-wave infrared radiation back toward space. Greenhouse gases. Molecules such as carbon dioxide, carbon tetrahydride, N2O, and water vapor absorb and re-emit infrared radiation, trapping heat in the atmosphere. Without the greenhouse effect, the average global temperature would be around -18 degrees Celsius, instead of the current +15 degrees Celsius. However, human activities have intensified this natural process, causing excessive warming. Key facts. CO2 levels have risen from 280 ppm, pre-industrial, to over 420 ppm today. Methane is 25 times more effective than carbon dioxide at trapping heat over a 100-year period. Nitrous oxide has 298 times the warming potential of CO2 over 100 years. Climate forcings and feedbacks. Climate systems respond to both forcings and feedback mechanisms. Climate forcings. Forcings are external factors that push the climate system toward warming or cooling. Anthropogenic forcings. Fossil fuel combustion, deforestation, industrial emissions. Natural forcings. Solar irradiance changes, volcanic eruptions, ocean circulation variations. Climate feedbacks. Feedbacks amplify or dampen the effects of forcings. Positive feedbacks. Ice albedo feedback. Melting ice reduces reflectivity, increasing solar absorption. Water vapor feedback. Warming increases atmospheric water vapor, enhancing greenhouse warming. Negative feedbacks. Cloud feedbacks. Certain clouds reflect sunlight, partially cooling the atmosphere. Feedback loops are critical for modeling future climate scenarios and predicting extreme events that affect the built environment. Observe changes in the climate system. Scientific measurements show that climate change is already occurring. Temperature trends. Global average surface temperature has increased by -1.1 degrees Celsius since 1850. Heat waves are more frequent, prolonged, and intense. Precipitation patterns. Shifts in rainfall distribution have caused flooding in some regions and droughts in others. Extreme rainfall events are increasing due to higher atmospheric moisture content. Cryosphere changes. Polar ice sheets and glaciers are retreating. Arctic sea ice has declined by over 40% since the 1970s. Sea level rise. Thermal expansion and melting ice contribute to -3.3 mm per year global sea level rise. Coastal cities face increased flooding risk and infrastructure damage. Ocean changes. Warming oceans contribute to more intense tropical cyclones. Ocean acidification threatens coral reefs and marine biodiversity. Extreme weather events. Climate change does not just cause gradual warming, it amplifies extreme events. Heat waves. Rising urban temperatures exacerbate the urban heat island effect. Floods and storms. Increased rainfall intensity and sea level rise amplify flood risk for urban areas. Droughts. Reduced water availability impacts agriculture and urban water supply. Wildfires. Higher temperatures and prolonged dry periods increase fire frequency and intensity. The built environment is particularly vulnerable to extreme weather. Buildings, transportation systems, and utilities may fail if not designed for new climate realities. Climate modeling. Climate models are essential for predicting future changes and informing mitigation strategies. They use mathematical representations of the atmosphere, oceans, land, and ice to simulate climate behavior. General circulation models, GCMs, simulate energy flows and climate processes on a global scale. Regional climate models, RCMs, provide higher resolution projections for specific regions or cities. Emission scenarios, models consider different pathways of greenhouse gas emissions, such as RCP 2.6, aggressive mitigation, low emissions. RCP 4.5 and RCP 6.0, intermediate scenarios. RCP 8.5, high emission business as usual scenario. By integrating these models, planners and engineers can anticipate changes in temperature, precipitation, sea level, and storm frequency to design resilient infrastructure. Linking climate science to the built environment. Understanding climate science is crucial for designing cities and buildings that can withstand current and future conditions. Urban planning, incorporating climate projections in zoning, flood management, and green space design. Building design, selecting materials and systems that tolerate heat, moisture, and wind extremes. Infrastructure resilience, upgrading bridges, roads, and utilities to withstand storms, sea level rise, and heat waves. By integrating scientific knowledge into planning and design, the built environment can transition from a source of vulnerability to a tool for climate adaptation. Summary. Climate change is driven primarily by human activities, particularly greenhouse gas emissions. Feedback loops, forcings, and complex climate interactions accelerate warming. Observed impacts include rising temperatures, sea level rise, altered precipitation, and extreme events. Climate models help predict future changes and guide resilient design strategies. The built environment must respond proactively to these changes to ensure safety, sustainability, and livability. References for Chapter 2. IPCC 2021, Climate Change 2021, The Physical Science Basis. Cambridge University Press. National Aeronautics and Space Administration, NASA, 2022, Global Climate Change, Vital Signs of the Planet. Trenberth, K.E. et al. 2015, Climate System Science, Observations and Modeling. Neal, G.A. et al. 2007, Global Climate Projections. Journal of Climate 2010, 2751-2769. Chapter 3, Impacts on Society and Infrastructure. Introduction. Climate change is not an abstract phenomenon, it has tangible effects on society, ecosystems, and the built environment. Rising temperatures, changing precipitation patterns, sea level rise, and extreme weather events increasingly threaten cities, transportation networks, utilities, and human health. Understanding these impacts is essential for architects, urban planners, engineers, and policymakers to design resilient and sustainable infrastructure. This chapter examines the multifaceted effects of climate change on society and the built environment, including urban heat islands, flooding, storm damage, and socioeconomic vulnerabilities. Impacts on human health. Climate change affects human health in multiple ways. Heat-related illnesses. Increased frequency and intensity of heat waves can cause heat exhaustion, heat stroke, and cardiovascular stress. Vulnerable populations, such as the elderly, children, and outdoor workers, are disproportionately affected. Urban areas experience amplified heat stress due to the urban heat island effect, where concrete, asphalt, and reduced vegetation trap heat. Vector-borne diseases. Warmer temperatures expand the range of mosquitoes, ticks, and other disease vectors. Diseases such as malaria, dengue, and Lyme disease are increasingly reported in regions previously too cold for these pathogens. Respiratory and allergic conditions. Increased air pollution and pollen concentrations exacerbate asthma and allergies. Wildfires, intensified by climate change, produce smoke that degrades air quality. Urban heat islands. Urban heat islands, UHIs, are areas where built environments retain more heat than surrounding rural regions. Factors contributing to UHIs include dense construction materials, concrete, asphalt, steel that absorb and store heat. Limited vegetation and tree cover. Waste heat from vehicles, industrial processes, and buildings. Consequences for the built environment. Increased cooling demands for buildings, leading to higher energy consumption. Accelerated deterioration of infrastructure, such as roads and rooftops. Health risks for urban residents during heat waves. Mitigation strategies include green roofs, reflective materials, urban forestry, and cool pavements. Flooding and sea level rise. Rising sea levels and changing rainfall patterns increase the risk of flooding in urban and coastal areas. Coastal flooding. Global sea level has risen approximately 3.3 millimeters per year, and projections estimate a rise of 0.3 to 1.1 meters by 2100. Low-lying cities such as Miami, Dhaka, and Jakarta face chronic inundation risks. Riverine flooding. Intense rainfall and extreme storm events cause rivers to overflow, damaging bridges, roads, and buildings. Flooding disrupts transportation, communication networks, and essential services. Storm surges. Hurricanes and typhoons produce surges that can devastate coastal infrastructure. Critical facilities such as power plants, hospitals, and water treatment plants are particularly vulnerable. Adaptation strategies include flood defenses, elevated structures, water-sensitive urban design, and resilient infrastructure planning. Impacts on infrastructure. Climate change threatens multiple types of infrastructure. Buildings. Extreme heat can warp materials and increase cooling energy demands. Flooding and storms can compromise structural integrity, foundations, and electrical systems. Transportation networks. Roads, railways, airports, and ports are susceptible to heat stress, flooding, and erosion. Permafrost melting in polar regions destabilizes roads and pipelines. Energy systems. Heat waves increase electricity demand for cooling, straining grids. Hydropower output may decline due to altered precipitation and water flow. Water and sanitation infrastructure. Flooding contaminates drinking water systems. Droughts reduce water availability for domestic, agricultural, and industrial use. Telecommunications. Storms and flooding damage fiber optic cables, cell towers, and data centers. Socioeconomic impacts. Climate change disproportionately affects communities based on geography, income, and social vulnerability. Low-income communities often reside in flood-prone areas or substandard housing, increasing exposure to climate hazards. Developing nations, limited financial and technical capacity hinders adaptation efforts. Economic costs, infrastructure damage, loss of productivity, and health impacts contribute to billions of dollars in annual losses globally. Migration and displacement. Rising seas and extreme weather force people to relocate, creating climate refugees and social tensions. Case studies of climate impacts. New York City, USA. Hurricane Sandy 2012 caused $19 billion in damages. Subway systems, tunnels, and coastal properties were heavily affected. Mumbai, India. Monsoon floods exacerbate traffic paralysis and damage slum housing. Urban drainage systems are frequently overwhelmed by extreme rainfall events. Venice, Italy. Sea level rise and storm surges threaten historical buildings and tourism-dependent infrastructure. Mo's Flood Barrier Project exemplifies large-scale adaptation engineering. Jakarta, Indonesia. Rapid subsidence and rising seas result in chronic flooding. The government plans to relocate the capital to a more resilient location. Linking impacts to the built environment. The built environment is both a contributor to and a victim of climate change. Urban development increases local temperatures and greenhouse gas emissions. Poorly designed infrastructure amplifies vulnerability to floods, storms, and heat. Integrating climate science with urban planning allows for proactive mitigation and adaptation. Key strategies include designing resilient buildings and infrastructure, implementing green infrastructure for stormwater management, utilizing renewable energy and energy-efficient systems, incorporating climate projections into urban planning. Summary: climate change has wide-ranging impacts on human health, cities, and infrastructure. Extreme heat, flooding, storms, and sea level rise threaten buildings, transportation networks, and energy systems. Vulnerable populations and low-income regions face disproportionate risks. Integrating climate science into urban planning and infrastructure design is essential for resilience. References for Chapter 3. IPCC 2022 Climate Change 2022 Impacts, Adaptation, and Vulnerability. Cambridge University Press. FEMA 2021 Climate Change and Infrastructure Risk. Rosenzweig, C. et al. 2018 Climate Change and Cities Second Assessment Report. Aerts, J.C. et al. 2014 Flood Resilience in Urban Areas, a Review. Chapter 4. Overview of the Built Environment. Introduction. The built environment encompasses all human-made spaces where people live, work, and move: buildings, roads, bridges, energy systems, and public spaces. It is both shaped by and shapes climate patterns. Understanding its components, materials, and functions is essential for designing resilient, sustainable, and low-carbon infrastructure in an era of climate change. This chapter provides an overview of the built environment, focusing on urbanization trends, building types, infrastructure systems, and materials. It also examines how the built environment contributes to greenhouse gas emissions and vulnerability to climate hazards. Components of the built environment. The built environment can be categorized into several interrelated components. Buildings. Residential, single-family homes, apartment complexes. Commercial, offices, retail spaces, industrial facilities. Institutional, schools, hospitals, government buildings. Transportation infrastructure. Roads, highways, bridges, and tunnels. Railways, subways, and ports. Airports and multimodal transit hubs. Utility systems. Water supply, wastewater, and stormwater systems. Energy generation, distribution, and storage. telecommunications, and digital networks. Public spaces and green infrastructure. Parks, greenbelts, and plazas. Flood control structures, wetlands, and urban forests. Each component interacts with others to form a complex urban ecosystem. Changes or damage to one system can cascade, affecting energy, transportation, and water availability. Urbanization and climate implications. Urbanization is a defining trend of the 21st century. Over 55% of the global population now lives in cities, projected to reach 68% by 2050. This growth has several implications. Energy demand. Concentrated populations increase heating, cooling, lighting, and transportation energy needs. Land use changes. Deforestation, wetland drainage, and soil sealing reduce natural carbon sinks and increase flood risk. Heat island effect. Dense construction amplifies local temperatures. Vulnerability to hazards. Coastal and floodplain cities face disproportionate risks from rising seas and storms. Urbanization emphasizes the need for climate-informed planning, including building codes, zoning, and green infrastructure. Building types and functions. Buildings are central to the built environment. They vary in purpose, design, and materials, all of which influence climate resilience. Residential buildings. Energy consumption for heating, cooling, and appliances constitutes the largest share of urban energy demand. Vulnerable populations may live in poorly insulated or structurally weak housing. Commercial and industrial buildings. Offices, factories, and retail spaces generate significant emissions through energy use and production processes. Industrial facilities may be located near rivers or coasts, exposing them to flooding and storms. Institutional buildings. Schools, hospitals, and emergency facilities must remain functional during extreme weather events. Resilience measures include backup energy, flood barriers, and structural reinforcement. High-rise versus low-rise construction. High-rise buildings require specialized energy and structural systems, often increasing embodied energy. Low-rise dispersed settlements may require more extensive transportation infrastructure. Infrastructure systems. Infrastructure provides the backbone of urban functionality. Transportation systems. Roads and railways are vulnerable to heat, floods, and erosion. Ports and airports face sea level rise, storm surges, and high wind events. Water and sanitation. Urban drainage, stormwater management, and wastewater treatment systems are critical for flood resilience. Droughts threaten water supply and urban agriculture. Energy infrastructure. Power generation and distribution are highly sensitive to temperature extremes and natural disasters. Energy grids must balance peak loads during heat waves or cold spells. Telecommunications and ICT. Reliable communications are essential for disaster response and urban management. Flooding, storms, and heat waves can disrupt networks and data centers. Materials in the built environment. The choice of construction materials significantly influences emissions, durability, and resilience. Concrete. Widely used for structural strength, contributes -8% of global carbon dioxide emissions. Vulnerable to cracking under heat and chemical attack from floodwaters. Steel. High strength-to-weight ratio, commonly used in high-rise buildings. Production is energy-intensive and carbon-heavy. Timber. Renewable and low carbon when sourced sustainably. Requires treatment to resist moisture, pests, and fire. Composites and modern materials. Glass, plastics, and advanced polymers offer energy-efficient insulation and durability. Environmental impacts depend on life cycle and recyclability. The built environment and greenhouse gas emissions. The built environment is a major contributor to climate change. Energy use. Heating, cooling, lighting, and appliances account for -28% of global energy-related carbon dioxide emissions. Construction materials, cement, steel, and aluminum production release significant greenhouse gases. Urban sprawl, expanding cities increase transportation emissions and reduce natural carbon sinks. Mitigating emissions requires integrating energy efficiency, low-carbon materials, renewable energy, and compact urban design. Linking the built environment to climate vulnerability. The built environment mediates the impacts of climate change. Exposure: buildings and infrastructure located in floodplains, coastal areas, or heat-prone regions are more vulnerable. Sensitivity: material choice, structural design, and urban density determine how infrastructure responds to stress. Adaptive capacity: cities and communities can mitigate risks through resilient design, emergency planning, and governance. Understanding the built environment's composition and function is a prerequisite for effective mitigation and adaptation strategies, explored in subsequent chapters. Summary: the built environment includes buildings, transportation, utilities, and public spaces. Urbanization, land use change, and material choice influence emissions and vulnerability. Infrastructure systems, water, energy, transportation, and ICT are highly sensitive to climate stressors. The built environment both contributes to and suffers from climate change, underscoring the need for resilient, low-carbon design. References for Chapter 4. UN Habitat, 2020, World Cities Report, The Value of Sustainable Urbanization. International Energy Agency, IEA, 2021, Global Status of Buildings and Construction. Lechner N. 2020, Heating, Cooling, Lighting, Sustainable Design Methods for Architects. Kennedy C. et al. 2015, The Role of Urban Infrastructure in Climate Resilience. Chapter 5, Energy Consumption in Buildings. Introduction. Buildings are a primary component of the built environment, and their energy use significantly contributes to global greenhouse gas emissions. Operational energy, used for heating, cooling, lighting, ventilation, appliances, and equipment, accounts for roughly 28% of global energy-related carbon dioxide emissions. In addition, embodied energy, which is the energy consumed in the extraction, manufacturing, and transportation of construction materials, adds another 11%. This chapter examines patterns of energy consumption in buildings, factors affecting energy demand, strategies for improving efficiency, and the integration of renewable energy. Understanding energy use in buildings is essential for mitigating climate change and designing resilient infrastructure. Patterns of energy consumption. Energy use in buildings varies by climate, building type, occupancy, and technology. Key patterns include residential buildings. Heating and cooling represent the largest share of energy consumption. Appliances, lighting, and water heating contribute substantially to electricity demand. Energy intensity varies widely depending on insulation, ventilation, and building materials. Commercial buildings. Office buildings, retail spaces, and hotels have high operational energy use due to lighting, HVAC systems, and electronic equipment. Peak energy demand often coincides with occupancy hours. Industrial buildings. Energy is used for process heating, machinery, and climate control. Energy efficiency improvements can significantly reduce operational costs and emissions. Institutional buildings. Schools, hospitals, and government facilities require reliable energy for operations and emergency functions. Critical systems such as backup power, lighting, and climate control are essential during extreme events. Factors affecting energy demand. Energy demand in buildings is influenced by multiple factors. Climate and geography. Hot climates require more cooling, cold climates more heating. Humidity, solar exposure, and wind patterns affect energy requirements. Building design and orientation. Building orientation affects solar heat gain and daylighting. Insulation, glazing, and envelope design determine heating and cooling loads. Occupancy behavior. User habits, appliance use, and thermostat settings influence energy consumption. Technological systems. HVAC systems, lighting technologies, and energy management systems directly affect energy efficiency. Building automation and smart controls optimize energy use. Energy efficiency strategies. Energy efficiency in buildings reduces greenhouse gas emissions, lowers operational costs, and improves comfort. Strategies include passive design measures, orientation and shading, minimize unwanted heat gain or loss. Insulation and envelope design, reduce energy needed for heating and cooling. Natural ventilation and daylighting, reduce reliance on mechanical systems. High-efficiency systems. Energy-efficient HVAC, lighting and appliances reduce electricity and fuel demand. Variable refrigerant flow systems and heat pumps improve climate control efficiency. Smart building technologies. Building automation systems monitor and control energy use. Sensors and IoT devices optimize lighting, temperature, and ventilation. Predictive maintenance reduces energy waste and extends equipment life. Behavioral interventions. Occupant education and awareness campaigns encourage energy-saving behaviors. Smart meters provide feedback on energy consumption patterns. Integration of renewable energy. Incorporating renewable energy in buildings reduces reliance on fossil fuels and supports carbon neutrality. Solar photovoltaic systems. Rooftop and facade-mounted PV systems generate electricity for building use. Net metering allows excess energy to be fed into the grid. Solar thermal systems. Used for water heating and space heating. Reduces demand for electricity and natural gas. Wind energy. Small-scale wind turbines can supplement building energy, particularly in rural or coastal areas. Geothermal systems. Ground source heat pumps provide efficient heating and cooling by leveraging the Earth's stable temperature. Energy storage. Batteries store surplus energy from renewable sources for use during peak demand or low generation periods. Building codes and standards. Government regulations and voluntary certification programs support energy efficiency. Building codes. Minimum energy performance standards for insulation, lighting, and HVAC systems. Climate-specific codes address local heating and cooling demands. Voluntary certifications. LEED, Leadership in Energy and Environmental Design, Green Building Rating System emphasizing energy efficiency. BREEAM, Building Research Establishment Environmental Assessment Method, focuses on sustainability performance. WELL Building Standard, integrates occupant health and energy performance. Compliance with codes and certifications helps reduce energy demand and emissions while promoting sustainable construction practices. Embodied energy considerations. While operational energy dominates a building's lifetime emissions, embodied energy, the energy used in material extraction, manufacturing, transport, and construction, can represent a significant portion of total carbon emissions. Cement, steel, and aluminum production are particularly carbon-intensive. Using recycled materials and low-carbon alternatives can significantly reduce embodied energy. Life Cycle Assessment, LCA, helps quantify environmental impacts from material selection to end-of-life disposal. Case studies. Edge Building, Amsterdam, Netherlands. Achieved net zero energy use through solar panels, efficient lighting, and intelligent building systems. One Angel Square, Manchester, UK. Uses a combined heat and power system, energy-efficient HVAC, and high-performance glazing to reduce energy consumption by 70% compared to conventional office buildings. The Bullitt Center, Seattle, USA. Designed as a net-zero energy commercial building with rainwater harvesting, solar PV, and passive solar design. Summary: buildings are a major contributor to greenhouse gas emissions due to operational and embodied energy use. Energy demand varies by climate, building type, and occupant behavior. Efficiency strategies include passive design, high-performance systems, smart controls, and renewable integration. Building codes, standards, and life cycle assessments guide sustainable design and construction. Net zero and low-carbon buildings demonstrate that energy-efficient design is feasible and scalable. References for Chapter 5. International Energy Agency, IEA, 2021, Global Status Report for Buildings and Construction. Perez Lombard, L. Ortiz, J. and Pout, C. 2008, A Review on Buildings' Energy Consumption Information. Energy and Buildings, 43, 394-398. U.S. Department of Energy, 2020, Energy Efficiency in Buildings. Kibert, C. 2016, Sustainable Construction, Green Building Design and Delivery. Chapter 6, Transportation and Urban Form. Introduction. Transportation and urban form are deeply intertwined with climate change. The way cities are designed, density, land use, and connectivity directly affects energy consumption, greenhouse gas emissions, and residents' vulnerability to climate hazards. Transportation accounts for approximately 24% of global carbon dioxide emissions, with the majority arising from road vehicles. This chapter explores the relationship between urban form and transportation, the climate impacts of mobility systems, and strategies for creating sustainable, low-carbon, and resilient cities. Urban form and its influence on transportation. Urban form refers to the spatial layout, density, and organization of a city. It has a direct impact on travel behavior and energy consumption. Compact cities. High-density, mixed-use developments reduce travel distances. Promote walking, cycling, and public transit. Lower per capita energy consumption and emissions. Sprawling cities. Low-density, single-use zoning increases dependency on private vehicles. Higher infrastructure costs for roads, utilities, and services. Greater energy consumption and greenhouse gas emissions per capita. Transit-oriented development, TOD. Focuses development around transit hubs. Encourages public transit use and reduces reliance on cars. Integrates residential, commercial, and recreational spaces for walkability. Transportation modes and emissions. Transportation systems contribute to emissions and climate impacts in various ways. Road transport. Cars, buses, and trucks are major sources of carbon dioxide, NOx, and particulate emissions. Private car dependence exacerbates congestion, air pollution, and fuel consumption. Rail transport. Trains, particularly electric rail, have lower emissions per passenger kilometer than cars. Freight rail reduces trucking emissions when efficiently utilized. Air transport. Aviation accounts for approximately 2-3% of global carbon dioxide emissions. High-altitude emissions have additional climate-forcing effects. Water transport. Shipping emissions, particularly from heavy fuel oil, contribute significantly to global greenhouse gases. Non-motorized transport. Walking and cycling produce zero direct emissions. Infrastructure such as bike lanes and pedestrian-friendly streets promotes sustainable mobility. Energy and climate implications of transportation systems. The design and operation of transportation networks influence urban energy demand and emissions. Vehicle miles traveled, VMT. Longer travel distances in sprawling cities increase fuel use and emissions. Congestion. Idling vehicles emit more pollutants and waste energy. Electrification. Electric vehicles, EVs, reduce emissions if the electricity comes from low-carbon sources. Modal shift. Encouraging public transit, cycling and walking lowers overall transportation emissions. Climate impacts on transportation infrastructure. Transportation infrastructure is vulnerable to climate hazards. Roads and bridges. High temperatures can cause asphalt deformation and concrete cracking. Flooding damages pavements, culverts, and bridges. Rail systems. Heat stress can warp tracks and disrupt signaling systems. Floods and landslides interrupt rail operations. Ports and airports. Sea level rise threatens coastal ports and airport runways. Storm surges and extreme winds disrupt operations. Public transit systems. Subways and light rail are vulnerable to flooding and heat stress. Service disruptions affect millions of daily commuters. Strategies for low-carbon and resilient transportation. Urban planning for reduced travel demand. Mixed-use zoning and compact neighborhoods minimize travel distances. TOD reduces dependence on private vehicles. Public transit improvements. Investment in reliable, accessible, and frequent transit reduces car use. Bus rapid transit, BRT, and metro systems improve mobility while lowering emissions. Active mobility infrastructure. Safe walking and cycling networks encourage non-motorized transport. Bike-sharing programs and pedestrian-friendly streets enhance adoption. Electrification and renewable energy. Transitioning to electric buses, rail, and vehicles reduces fossil fuel emissions. Integration with renewable electricity maximizes climate benefits. Climate-resilient infrastructure design. Elevated roads, permeable pavements, and stormwater management reduce flood risks. Heat-resistant materials prolong infrastructure lifespan. Case studies. Copenhagen, Denmark. Over 40% of trips are by bike. Extensive cycling infrastructure reduces traffic congestion and emissions. Curitiba, Brazil. Bus rapid transit system efficiently moves residents while lowering car dependency. Integrated urban planning and transit-oriented development promote compact growth. Singapore. High-density, mixed-use development combined with mass transit reduces per capita transport emissions. Green transport initiatives include electric buses, bike-sharing, and car-sharing schemes. Linking urban form, transport, and climate. Urban form and transportation are critical leverage points for climate mitigation and adaptation. Compact, walkable cities reduce energy use and emissions. Resilient infrastructure ensures functionality during extreme weather events. Integrating land use, transport planning, and renewable energy maximizes sustainability and livability. Designing cities with climate considerations improves mobility, reduces emissions, and protects infrastructure from future climate hazards. Summary. Urban form strongly influences transportation energy demand and emissions. Sprawling cities increase car dependence and greenhouse gas emissions, while compact transit-oriented cities reduce them. Transportation infrastructure is vulnerable to heat, floods, storms, and sea level rise. Low-carbon strategies include public transit, active mobility, electrification, and climate-resilient infrastructure. Integrated urban planning and transport systems are essential for sustainable, resilient cities. References for Chapter 6. United Nations 2019, World Urbanization Prospects. International Transport Forum 2020, Transport Outlook 2020. Newman P. and Kenworthy, J. 2015, The End of Automobile Dependence. C40 Cities 2018, Climate Action in Cities, Transportation Strategies. Chapter 7, Designing for Resilience. Introduction. Climate change is no longer a distant threat. It is a present reality affecting cities and infrastructure worldwide. Designing for resilience means preparing buildings, infrastructure, and urban systems to withstand extreme weather, sea level rise, heat waves, and other climate hazards while maintaining functionality. Resilient design goes beyond disaster response. It integrates adaptation into the planning, construction, and operational stages of the built environment. This chapter examines principles, strategies, and case studies for climate-resilient design in buildings and urban areas. Principles of resilient design. Redundancy. Critical systems, energy, water, transport, should have backups to maintain function during disruptions. Robustness. Structures should withstand extreme events, including high winds, floods, and heat. Flexibility and adaptability. Buildings and urban systems should accommodate changing climate conditions over time. Resource efficiency. Efficient use of energy, water, and materials reduces environmental impact while increasing resilience. Integration with nature. Incorporating natural systems, such as wetlands and green infrastructure, enhances resilience and provides co-benefits like cooling and biodiversity. Flood-resilient design. Flooding is one of the most common climate-related hazards affecting the built environment. Strategies include elevated structures. Buildings, utilities, and critical infrastructure can be raised above predicted flood levels. Waterproofing and flood barriers. Flood-resistant materials, sealants, and barriers prevent water ingress. Urban drainage systems. Stormwater management through permeable pavements, green roofs, retention ponds, and rain gardens reduces runoff. Flood zoning and planning. Avoid building in high-risk floodplains or implement strict building codes in vulnerable areas. Case study. The Netherlands Delta Works System combines dikes, storm surge barriers, and water management infrastructure to protect urban areas from flooding. Heat-resilient design. Increasing temperatures and urban heat islands threaten human health and building performance. Heat-resilient strategies include cool roofs and reflective materials. Reduce heat absorption and indoor cooling demand. Green roofs and urban forestry. Vegetation provides shading, evapotranspiration cooling, and stormwater absorption. Natural ventilation and passive cooling. Building orientation, shading devices, and cross-ventilation reduce reliance on air conditioning. Heat-resilient public spaces. Shaded parks, water features, and tree-lined streets protect urban populations during heat waves. Case study. Singapore's City in a Garden initiative integrates green infrastructure and building greenery to mitigate heat stress in dense urban areas. Storm-resistant design. High winds, hurricanes, and typhoons can cause catastrophic damage to buildings and infrastructure. Storm-resistant strategies include structural reinforcement. Wind-resistant design, reinforced concrete and steel framing enhance building robustness. Impact-resistant materials. Laminated glass, hurricane shutters, and resilient roofing materials reduce damage from flying debris. Redundant utilities. Backup generators, water storage, and microgrids maintain critical services during storm events. Case study. Japan's earthquake and typhoon-resistant buildings combine flexible structural systems with advanced materials to withstand natural hazards. Coastal and sea level rise adaptation. Rising seas threaten coastal cities, infrastructure, and ecosystems. Adaptive strategies include seawalls, levees, and dikes. Physical barriers protect low-lying urban areas from storm surges. Managed retreat. Relocating vulnerable populations and infrastructure from high-risk zones reduces long-term exposure. Elevated infrastructure. Roads, railways, and utilities are elevated to maintain functionality during flooding. Ecosystem-based solutions. Restoring mangroves, wetlands, and dunes buffers waves, absorbs floodwaters, and enhances biodiversity. Case study. New York City's post-Hurricane Sandy flood resilience measures include elevated subway entrances, storm surge barriers, and wetland restoration along the coastline. Integrating resilience in urban planning. Risk assessment and mapping. Identify hazards, vulnerabilities, and critical infrastructure at city and neighborhood scales. Climate-informed zoning. Limit development in high-risk areas and encourage resilient building practices. Green infrastructure networks. Parks, green corridors, and retention basins reduce flooding and heat stress. Community engagement. Public participation enhances preparedness and ensures social equity in resilience planning. Monitoring and early warning systems. Sensors, IoT networks, and predictive modeling support timely responses to extreme events. Multi-hazard resilience. Resilient design must consider multiple hazards simultaneously. Buildings may face floods, heat waves, and high winds. Critical infrastructure must function under overlapping stressors. Systems thinking allows planners and engineers to design integrated solutions that reduce cascading failures. Example: multi-hazard resilience is applied in Tokyo, where buildings, utilities, and transportation networks are designed to withstand earthquakes, typhoons, and heat stress simultaneously. Summary: resilient design prepares the built environment to withstand climate hazards while maintaining functionality. Key principles include redundancy, robustness, adaptability, resource efficiency, and integration with nature. Flood, heat, storm, and coastal resilience strategies are essential for protecting urban populations and infrastructure. Urban planning, community engagement, and multi-hazard approaches enhance citywide resilience. Case studies from the Netherlands, Singapore, New York, and Japan demonstrate practical applications of resilient design. References for Chapter 7. Aerts J. et al. 2014, Flood Resilience in Urban Areas, a Review. UN Habitat, 2020, World Cities Report, The Value of Sustainable Urbanization. FEMA 2021, Designing for Resilience, Best Practices for Buildings and Infrastructure. Miro S. Newell J.P. and Stultz M. 2016, Defining Urban Resilience, a Review. Chapter 8, Sustainable Materials and Construction. Introduction. The construction sector is one of the largest contributors to global greenhouse gas emissions, responsible for approximately 11% of global carbon dioxide emissions through material production and construction activities. Sustainable materials and construction practices are essential for reducing environmental impacts, improving resilience, and promoting a circular economy. This chapter explores the selection of low-carbon materials, innovative construction techniques, and strategies for sustainable building design, with an emphasis on their role in mitigating climate change and enhancing the built environment's resilience. Principles of sustainable construction. Sustainable construction integrates environmental, social, and economic considerations throughout the building life cycle. Core principles include: minimizing resource use. Reduce consumption of raw materials and energy during construction and operation. Maximizing efficiency. Use high-performance materials and technologies that improve building longevity and energy performance. Reducing environmental impact. Select low-carbon and low-embodied energy materials. Minimize waste, pollution, and emissions during construction. Promoting circular economy. Reuse, recycle, and repurpose materials at the end of their life cycle. Design for disassembly and adaptability. Resilience and durability. Ensure materials withstand climate hazards, reducing maintenance and replacement needs. Low carbon and sustainable materials. Concrete alternatives. Traditional concrete contributes -8% of global carbon dioxide emissions. Low carbon alternatives. Geopolymer concrete using fly ash or slag. Carbon-cured concrete that sequesters carbon dioxide during curing. Recycled aggregate concrete to reduce virgin material use. Steel and metals. Steel production is energy-intensive and carbon-heavy. Strategies. Use recycled steel in construction. Optimize structural design to reduce steel volume. Adopt green steel production methods using renewable energy and hydrogen. Timber and engineered wood. Renewable, carbon-sequestering material when sourced responsibly. Cross-laminated timber, CLT, enables high-rise construction with lower carbon emissions. Forest certification, FSC-PEFC, ensures sustainable sourcing. Insulation and building envelope materials. Natural insulation, cork, sheep wool, cellulose, reduces embodied energy. High-performance glazing minimizes heat loss and gain. Finishes and non-structural materials. Use low VOC paints, adhesives and coatings to reduce indoor air pollution. Recycled and locally sourced, finishes lower transportation emissions. Innovative construction methods. Prefabrication and modular construction. Factory-built components reduce waste, construction time and energy use. Modular construction allows future adaptation and disassembly. 3D printing in construction. Enables precise material use, reduces waste, and allows complex structural designs with lower embodied energy. Green roofs and living walls. Improve insulation, reduce urban heat islands and manage stormwater. Enhance building aesthetics and biodiversity. Adaptive and flexible design. Buildings designed for future retrofits and material reuse reduce the need for demolition. Life cycle assessment, LCA, and carbon accounting. Life cycle assessment evaluates the environmental impact of materials and construction processes. Stages considered. Material extraction and processing. Construction and assembly. Operation and maintenance. End of life, demolition, recycling, and disposal. Benefits of LCA. Identifies high-impact materials and processes. Informs decisions for low-carbon alternatives. Supports compliance with sustainability certifications, LEED BREEAM. Waste reduction and circular economy. Construction and demolition waste management. Segregate, recycle, and reuse materials such as concrete, steel, and timber. Designed for disassembly. Buildings designed for easy deconstruction facilitate material recovery. Material passports. Track material properties and origins to improve recycling and reuse potential. Circular construction practices. Reuse of prefabricated components, adaptive reuse of structures, and integration of recycled materials in new projects. Case studies. Bullitt Center, Seattle, USA. Uses FSC-certified timber, recycled steel, and low-carbon concrete. Designed for disassembly and net-zero energy operation. T3 Building, Minneapolis, USA. Mass timber structure reduces embodied carbon by -50% compared to conventional steel and concrete construction. BedZED, London, UK. Uses recycled materials, low-carbon concrete, and energy-efficient systems. Incorporates green roofs and on-site renewable energy. Linking materials and construction to climate resilience. Material selection affects durability under climate hazards such as heat, floods, and storms. Sustainable construction reduces the carbon footprint while enhancing building lifespan and resilience. Combining low-carbon materials with resilient design strategies amplifies climate mitigation and adaptation benefits. Summary. Sustainable construction minimizes environmental impact and supports climate resilience. Low-carbon materials include timber, recycled steel, low-carbon concrete, and natural insulation. Innovative construction methods such as prefabrication, modular construction, and 3D printing, reduce waste and embodied energy. Life cycle assessment guides material selection and design decisions. Circular economy principles promote material reuse, disassembly, and long-term sustainability. Integrating sustainable materials with resilient design enhances both climate mitigation and adaptation in the built environment. References for Chapter 8. Kybert C. 2016, Sustainable Construction, Green Building Design and Delivery. International Energy Agency IEA, 2020, The Role of Materials in Low-Carbon Construction. World Green Building Council 2019, Advancing Net Zero, Whole Life Carbon Roadmap. Ding GKC 2008, Sustainable Construction, The Role of Environmental Assessment Tools. Chapter 9, Policy and Governance. Introduction. Effective climate action in the built environment requires more than technical solutions. It requires robust policy frameworks, governance structures, and regulatory instruments. Governments, municipalities, and international bodies play a crucial role in establishing standards, incentives, and enforcement mechanisms to promote low-carbon, resilient urban development. This chapter explores the policies, regulations, and governance strategies that influence sustainable construction, energy efficiency, urban planning, and climate adaptation. International policy frameworks. United Nations Framework Convention on Climate Change, UNFCCC. Established in 1992 to coordinate global climate action. Sets the foundation for binding agreements, such as the Kyoto Protocol and Paris Agreement. Paris Agreement, 2015. Aims to limit global temperature rise to well below 2 degrees Celsius, pursuing 1.5 degrees Celsius if possible. Countries submit nationally determined contributions, NDCs, outlining emission reduction targets. Encourages integrating climate adaptation into urban planning and infrastructure development. Sustainable Development Goals, SDGs. 11 Sudanese pounds. Sustainable Cities and Communities emphasizes resilient, inclusive, and sustainable urbanization. 13 Sudanese pounds. Climate action promotes climate mitigation and adaptation measures. National building codes and standards. National governments implement policies to ensure energy efficiency, safety, and resilience. Energy efficiency codes. Minimum performance standards for heating, cooling, lighting, and appliances. Example, ASHRAE standards in the United States, Part L building regulations in the UK. Resilient building codes. Regulations for flood-prone, earthquake-prone, or hurricane-prone areas. Specify structural requirements, materials, and design practices for hazard resistance. Green building certifications. Voluntary programs such as LEED, BREEAM, and WELL encourage sustainable design beyond minimum code requirements. Incentives may include tax breaks, expedited permitting, or higher property valuations. Urban planning policies. Urban governance shapes land use, transportation, and infrastructure to mitigate climate impacts. Zoning and land use planning. Limit development in floodplains, coastal areas, or high-risk zones. Promote mixed-use, compact, and transit-oriented development. Public transit and active mobility policies. Investment in mass transit reduces car dependency and emissions. Bike lanes, pedestrian streets, and shared mobility programs encourage low-carbon transportation. Green infrastructure and open space policies. Mandates or incentives for parks, urban forests, green roofs, and permeable surfaces improve resilience and livability. Climate adaptation and disaster risk governance. Effective adaptation requires integrated policies and emergency preparedness. Hazard mapping and risk assessment. Identify vulnerable areas and critical infrastructure. Inform zoning, building codes, and emergency planning. Disaster response planning. emergency shelters, evacuation routes, and disaster management protocols. Coordination between national, regional, and local agencies. Funding and incentives for resilience. Subsidies, low-interest loans, and insurance programs encourage resilient building practices. Incentives for sustainable construction. Policy instruments can accelerate the adoption of low-carbon and resilient construction. Financial incentives. Tax credits for energy-efficient buildings and renewable energy installations. Grants and subsidies for retrofitting existing structures. Regulatory incentives. Streamline permitting for sustainable projects. Mandates for using recycled or low-carbon materials. Market-based instruments. Carbon pricing or emissions trading systems incentivize reduction of building-related emissions. Governance challenges. Fragmentation of responsibilities. Multiple agencies, energy, housing, transport, environment, may lack coordination. Limited enforcement. Building codes and environmental regulations may not be consistently enforced. Resource constraints. Developing nations may lack technical, financial, or institutional capacity for implementation. Equity and inclusivity. Policies must ensure vulnerable populations benefit from climate adaptation measures. Case studies. Germany, energy-efficient buildings and EV. National building regulations require high energy performance. Incentives for retrofitting older buildings with efficient systems and insulation. Singapore Green Mark Scheme. Voluntary certification program encouraging energy-efficient, sustainable, and resilient buildings. Linked to tax incentives, grants, and public recognition. New York City, climate resiliency programs. Post-Hurricane Sandy, NYC implemented flood protection, zoning adjustments, and infrastructure upgrades. Comprehensive planning integrates resilience into urban development policies. Integrating policy with design and planning. Policies and governance frameworks are most effective when integrated with design and planning practices. Coordination between stakeholders ensures resilience measures are implemented across buildings, transport, and utilities. Incentivizing low-carbon and resilient construction accelerates adoption. Monitoring and evaluation ensures policies achieve intended climate mitigation and adaptation goals. International collaboration supports knowledge transfer, technical assistance, and funding for sustainable urban development. Summary. Policy and governance are critical drivers of sustainable and resilient urban development. International frameworks, Paris Agreement SDGs set overarching climate goals. National building codes, green certifications, and urban planning policies translate climate goals into actionable standards. Financial, regulatory, and market-based incentives encourage low-carbon and resilient construction. Effective governance requires coordination, enforcement, and consideration of equity and inclusivity. Case studies from Germany, Singapore, and New York demonstrate successful integration of policy and design. References for Chapter 9. UN Habitat, 2020, World Cities Report, The Value of Sustainable Urbanization. International Energy Agency, IEA, 2020, Buildings and Climate Policy, Global Trends. C40 Cities 2018, Urban Policy and Climate Action Strategies. Roberts D. 2010, Prioritizing Climate Change Adaptation in Urban Policy. Chapter 10, Mitigation Strategies for the Built Environment. Introduction. Mitigation in the built environment involves reducing energy consumption, lowering greenhouse gas emissions, and minimizing environmental impacts across the life cycle of buildings and infrastructure. Achieving these objectives is essential for meeting climate targets, including the Paris Agreement's goal of limiting global warming to well below 2 degrees Celsius. This chapter explores strategies for emission reduction, energy efficiency, sustainable urban planning, low-carbon materials, and renewable energy integration. Energy efficiency in buildings. Energy efficiency is the cornerstone of mitigation strategies. Passive design measures. Optimize building orientation for solar gain. Use high-performance insulation and glazing. Maximize natural ventilation and daylighting. Efficient HVAC systems. Variable refrigerant flow (VRF) systems, heat pumps and high-efficiency boilers. Regular maintenance ensures optimal performance and reduces energy waste. Lighting and appliances. LED lighting, energy-efficient appliances, and smart controls lower operational energy use. Building automation and smart systems. Sensors and IoT devices optimize heating, cooling, lighting, and ventilation. Predictive maintenance reduces energy losses and equipment failures. Renewable energy integration. Transitioning to renewable energy reduces dependence on fossil fuels. Solar photovoltaic (PV) systems. Rooftop and facade PV systems provide on-site electricity. Can be combined with net metering for surplus energy feed-in. Solar thermal systems. Efficient water and space heating reduces reliance on gas and electricity. Wind energy. Small-scale urban wind turbines supplement building energy. Geothermal and ground source heat pumps provide heating and cooling with lower energy use than conventional systems. Energy storage. Batteries and thermal storage allow buildings to manage demand and reduce peak emissions. Sustainable urban planning. Urban form and planning significantly influence energy use and emissions. Compact and mixed-use development. Reduces travel distances, encourages walking, cycling, and public transit. Transit-oriented development, TOD. Concentrates development around transit hubs to minimize car dependency. Green infrastructure. Parks, green roofs, and urban forests mitigate heat islands, absorb carbon, and manage stormwater. Zoning and land use policies. Encourage density, reduce sprawl, and preserve natural areas to maintain carbon sinks. Low carbon and circular materials. Material selection reduces embodied carbon. Low-carbon concrete and steel. Geopolymer concrete, recycled steel, and green production methods reduce emissions. Timber and engineered wood. Cross-laminated timber, CLT, stores carbon and reduces reliance on steel and concrete. Recycled and locally sourced materials. Minimize transportation emissions and construction waste. Circular economy practices. Design for disassembly, material reuse, and recycling reduces life cycle carbon. Retrofitting existing buildings. Existing buildings account for a significant portion of urban emissions. Envelope upgrades. Insulation, high-performance windows, and air sealing reduce heating and cooling demand. HVAC and lighting replacement. Energy-efficient systems lower operational energy and improve comfort. Renewable integration. Solar PV, solar thermal, and small-scale wind or geothermal installations retrofit older buildings. Smart controls. Automated energy management optimizes retrofitted buildings' performance. Case study. The Empire State Building retrofit reduced energy consumption by 38% using insulation, high-performance windows, and efficient lighting. Carbon accounting and monitoring. Measuring emissions is essential for mitigation. Building energy audits. Identify energy use patterns and inefficiencies. Life cycle carbon assessment (LCA). Quantifies embodied and operational emissions over a building's lifetime. Carbon reporting and certification. Programs like LEED, BREEAM, and EDGE track and verify reductions. Digital twins and IoT monitoring. Real-time monitoring enables continuous improvement and predictive maintenance. Policy and incentives for mitigation. Government policies and incentives accelerate adoption of mitigation strategies. Energy efficiency standards and codes. Minimum performance standards for new and existing buildings. Financial incentives. Tax credits, grants, and low-interest loans encourage retrofits and renewable integration. Market-based mechanisms. Carbon pricing and emissions trading incentivize reduced operational and embodied carbon. Voluntary certification programs. Recognize high-performance buildings and encourage replication of best practices. Case studies of mitigation strategies. 1 Angel Square, Manchester, UK. Net zero energy design with high-performance envelope, combined heat and power and natural ventilation. Bullitt Center, Seattle, USA. Net zero energy and water, sustainable timber construction and composting waste systems. Masdar City, Abu Dhabi, UAE. Planned low-carbon city using solar PV, energy-efficient buildings, and electric mobility systems. Summary. Mitigation strategies focus on reducing energy consumption, operational and embodied emissions, and overall environmental impact. Energy efficiency, passive design, and renewable integration are central to low-carbon buildings. Sustainable urban planning, compact cities, and transit-oriented development reduce emissions from transport and energy use. Low-carbon materials, circular economy practices, and retrofitting of existing buildings minimize embodied carbon. Carbon accounting, monitoring, and policy incentives ensure measurable and verifiable mitigation outcomes. References for Chapter 10. International Energy Agency (IEA) 2021, Net Zero by 2050, Building Sector Strategies. Kybert C. 2016, Sustainable Construction, Green Building Design and Delivery. World Green Building Council 2019, Advancing Net Zero, Whole Life Carbon Roadmap. Perez Lombard, L. Ortiz, J. and Pout C. 2008, A Review on Buildings' Energy Consumption Information. Chapter 11, Financing Climate Resilient and Low-Carbon Infrastructure. Introduction. Transitioning the built environment toward climate-resilient and low-carbon systems requires significant investment. Financing is a critical enabler of mitigation and adaptation strategies, encompassing public, private, and blended funding sources. Without adequate financial mechanisms, even the most technically feasible solutions may not be realized. This chapter explores funding models, financial instruments, investment challenges, and case studies of successful financing for sustainable urban infrastructure. Investment needs. Global infrastructure gap. The UN estimates that by 2030, $94 trillion is needed globally for sustainable infrastructure. Urban areas require investment in energy-efficient buildings, resilient transport, water management, and renewable energy integration. Climate adaptation and resilience. Investments are needed in flood defenses, storm-resilient infrastructure, heat mitigation, and emergency systems. Adaptation finance is particularly critical in developing countries vulnerable to climate hazards. Low-carbon construction and retrofitting. Upgrading existing building stock to net zero energy performance requires large-scale capital investment. Financing energy-efficient materials, renewable systems, and green roofs supports mitigation goals. Public sector financing. Governments play a pivotal role in providing capital and incentives for sustainable infrastructure. Budget allocations and grants. Direct government funding for green infrastructure, resilient transport, and public buildings. Tax incentives. Tax credits and deductions for energy-efficient construction, renewable energy installations, and retrofits. Public-private partnerships, PPPs. Collaborations between governments and private investors to finance large-scale infrastructure projects. Share risks, leverage expertise, and reduce upfront government expenditure. Green bonds. Government-issued bonds, specifically for financing environmentally sustainable projects. Private sector investment. The private sector can provide substantial funding and innovation. Corporate sustainability investment. Businesses invest in low-carbon facilities, energy efficiency, and renewable energy to reduce operational costs and improve brand value. Green real estate funds. Funds focused on energy-efficient, resilient buildings generate financial returns and environmental benefits. Venture capital and private equity. Support emerging technologies for energy-efficient construction, smart grids, and climate-resilient materials. Blended finance and international funding. Blended finance leverages multiple sources to reduce risk and attract investment. Development banks and multilateral institutions. World Bank, Asian Development Bank, and European Investment Bank provide loans, grants, and guarantees for sustainable infrastructure. Climate funds. Green Climate Fund, GCF, and Global Environment Facility, GEF, support climate adaptation and mitigation projects, particularly in developing countries. Risk mitigation instruments. Credit enhancements, guarantees, and insurance products reduce perceived financial risks for private investors. Innovative financial instruments. Energy performance contracts, EPCs. Third-party investors finance energy efficiency upgrades, recouping costs through energy savings. Property-assessed clean energy, PACE financing. Enables building owners to finance energy improvements via property tax assessments. Climate resilience bonds. Bonds specifically issued to fund infrastructure projects that enhance resilience to extreme weather and climate risks. Green banks and revolving funds. Public or quasi-public institutions that provide low-interest loans to scale low-carbon and resilient technologies. Cost-benefit analysis and economic justification. Quantifying benefits. Reduced energy costs, lower emissions, avoided disaster damage, and improved public health. Life cycle costing. Evaluates long-term costs and benefits, including operational and maintenance savings from energy efficiency and resilience measures. Return on investment, ROI. Demonstrates financial feasibility of sustainable construction, retrofits, and adaptation projects. Risk-adjusted valuation. Considers climate risks, regulatory changes, and market dynamics when evaluating investment decisions. Case studies. New York City Green Infrastructure Program. Public investment in green roofs, permeable pavements, and stormwater management reduced flood risk and improved water quality. Masdar City, UAE. Funded through a combination of government investment, private equity, and international finance to achieve low-carbon urban development. London Green Bonds. Issued to fund energy-efficient public buildings, renewable energy installations, and sustainable transport projects. Challenges and barriers. High upfront costs. Sustainable and resilient infrastructure often requires significant initial capital. Limited access to financing. Small-scale projects or developing regions may face difficulty obtaining affordable loans. Policy and regulatory uncertainty. Investors require stable regulations and clear incentives for long-term commitments. Technical capacity gaps. Lack of expertise in designing, implementing, and maintaining sustainable infrastructure can deter investment. Summary. Financing is critical for implementing climate-resilient and low-carbon infrastructure. Public sector, private sector, blended finance, and international funding mechanisms provide the necessary capital. Innovative instruments such as green bonds, EPCs, and PACE financing reduce financial barriers. Cost-benefit analysis and life cycle costing demonstrate economic viability and encourage investment. Case studies from New York City, Masdar City, and London highlight successful financing models. Overcoming barriers requires stable policy, technical capacity building, and innovative financial mechanisms. References for Chapter 11. United Nations Environment Programme, UNEP, 2020, Financing Sustainable Cities. World Bank 2019, Investing in Climate Resilient Infrastructure. Climate Policy Initiative 2020, Global Landscape of Climate Finance. OECD 2018, Financing Climate Action in Cities. Chapter 12, Monitoring, Evaluation and Reporting for Sustainable Built Environments. Introduction. Monitoring, evaluation and reporting, MER, are essential components of sustainable urban development and climate action. They ensure that policies, projects, and investments in the built environment achieve intended outcomes, such as reducing greenhouse gas emissions, improving energy efficiency, and enhancing resilience. This chapter examines MER frameworks, methodologies, and tools used in the built environment, emphasizing data-driven decision-making, transparency, and accountability. Importance of MER in the built environment. Accountability ensures that public funds and private investments are effectively used. Demonstrates compliance with regulations, building codes, and sustainability standards. Performance tracking measures energy use, emissions, water consumption, and waste generation. Evaluates the effectiveness of mitigation and adaptation strategies. Informed decision-making identifies successful strategies and areas needing improvement. Supports evidence-based policy and design adjustments. Stakeholder engagement. Transparent reporting builds trust with investors, communities, and regulatory bodies. Monitoring. Monitoring involves systematic, continuous measurement of key performance indicators, KPIs. Energy and carbon monitoring. Track electricity, gas, and fuel consumption. Measure operational and embodied carbon emissions. Use smart meters, IoT sensors, and building management systems. Water and waste monitoring. Track water consumption, wastewater generation, and recycling rates. Measure the effectiveness of rainwater harvesting, greywater reuse, and waste management systems. Climate and resilience monitoring. Track flood events, heatwave impacts, and building performance under extreme weather. Monitor adaptive measures such as stormwater management systems, green roofs, and cooling strategies. Occupant behavior monitoring. Track occupancy patterns, thermostat settings, and equipment use. Inform behavior-based energy-saving programs. Evaluation. Evaluation assesses whether strategies and interventions meet predefined objectives. Performance assessment. Compare actual energy, water, and emissions data against targets. Evaluate resilience measures against observed climate events. Life cycle assessment, LCA. Evaluate environmental impacts of materials and construction over the building's life cycle. Cost-benefit analysis. Assess economic efficiency of mitigation, adaptation, and sustainability interventions. Benchmarking. Compare buildings, projects, or cities against industry standards, historical performance, or similar developments. Reporting. Reporting communicates findings to stakeholders and ensures compliance. Internal reporting. Facility managers and building owners track operational performance and identify areas for improvement. Regulatory reporting. Compliance with national building codes, energy regulations, and carbon reporting standards. Voluntary reporting and certification. LEED BREEAM EDGE, and WELL certifications require periodic reporting. Corporate sustainability reports disclose environmental performance metrics to investors and the public. Digital dashboards and data visualization. Real-time dashboards display energy, water, emissions, and resilience KPIs. Supports timely interventions and transparency. Tools and methodologies. Building management systems (BMS). Automate monitoring and control of HVAC, lighting, and energy systems. Enable predictive maintenance and performance optimization. IoT sensors and smart devices. Collect granular data on occupancy, energy use, indoor air quality, and water consumption. Life cycle assessment software. Tools like SEMA Pro, Gabi, and Tally quantify embodied and operational carbon. Greenhouse gas accounting standards. ISO 14064, GHG Protocol, and National Carbon Accounting Standards guide emissions measurement. Urban monitoring platforms. Platforms integrate multiple data streams, transport, energy, climate, population, for city-scale evaluation. Challenges in MER. Data quality and availability. Inconsistent, incomplete, or outdated data can compromise accuracy. Technical capacity. Limited expertise in monitoring systems, software, and data analysis. Cost constraints. Sensors, software, and monitoring programs may be expensive, especially for small-scale or developing region projects. Standardization. Diverse metrics, methods, and reporting frameworks can hinder comparability and benchmarking. Behavioral uncertainty. Occupant behavior and operational practices influence building performance, complicating evaluation. Best practices for effective MER. Define clear KPIs. Align monitoring metrics with climate mitigation and adaptation objectives. Integrate MER in design and planning. Consider monitoring needs during building design and urban planning stages. Leverage digital technologies. Use IoT, BMS, and cloud platforms for continuous automated data collection and analysis. Periodic evaluation and feedback. Conduct regular assessments and adjust strategies based on findings. Stakeholder engagement and transparency. Share results with communities, investors, regulators, and other stakeholders. Case studies. Edge Building, Amsterdam, Netherlands. Smart sensors monitor lighting, temperature, and occupancy. Data-driven optimization reduced energy use by 70% compared to conventional office buildings. Singapore's Smart Nation Initiative. Urban monitoring platforms track energy, water, and transport systems at city scale. Data informs policy, emergency response, and sustainability programs. Empire State Building retrofit, New York, USA. Continuous monitoring of energy use and indoor conditions informs performance improvements and verifies energy savings. Summary. Monitoring, evaluation, and reporting, MER, are essential for sustainable and resilient built environments. MER ensures accountability, tracks performance, supports decision-making, and engages stakeholders. Effective monitoring involves energy, water, waste, climate resilience, and occupant behavior data collection. Evaluation assesses whether interventions meet objectives using benchmarks, life cycle assessment, and cost-benefit analysis. Reporting communicates outcomes for compliance, certification, and transparency. Tools such as BMS, IoT sensors, LCA software, and digital dashboards enhance MER effectiveness. Case studies demonstrate how data-driven approaches lead to measurable energy savings and improved resilience. References for Chapter 12. International Energy Agency, IEA, 2020, Monitoring and Verification of Energy Performance in Buildings. UN Habitat, 2020, World Cities Report, Data for Sustainable Urbanization. ISO 14064-2018, Greenhouse Gas Accounting Standards. Edge Technologies 2019, Smart Building Case Studies. Chapter 13, Community Engagement and Behavior Change. Introduction. Sustainable and climate-resilient cities are not built solely through technology and regulation. They rely heavily on the behavior and participation of communities. Residents, building occupants, and local stakeholders influence energy use, water consumption, waste generation, and the effectiveness of adaptation measures. This chapter examines strategies for engaging communities, promoting behavior change, and fostering social acceptance of climate mitigation and adaptation measures in the built environment. Importance of community engagement. Enhancing effectiveness of interventions. Community involvement ensures that projects meet local needs and are practically implementable. Promoting ownership and stewardship. Engaged communities are more likely to maintain and care for green infrastructure, renewable systems, and resilience measures. Facilitating behavior change. Participation in sustainability initiatives encourages energy saving, water conservation, recycling, and low-carbon transportation habits. Equity and inclusivity. Involving marginalized groups ensures that adaptation and mitigation strategies are socially equitable and accessible. Methods of community engagement. Public consultations and workshops. Gather input on urban planning, green infrastructure projects, and building designs. Build consensus and address local concerns. Participatory planning. Citizens co-create solutions for sustainable neighborhoods, transportation systems, and public spaces. Education and awareness campaigns. Inform residents about energy efficiency, climate risks, and sustainable behaviors. Use multimedia campaigns, workshops, and school programs. Citizen science and data collection. Residents contribute to monitoring air quality, energy use, or flood risks. Increases engagement and provides valuable data for decision-making. Promoting behavior change. Nudging and incentives. Use subtle cues or default options to encourage sustainable behaviors, e.g., energy-efficient thermostats, recycling stations. Financial incentives, such as rebates for energy-efficient appliances, increase adoption. Feedback and information. Real-time energy and water usage dashboards encourage conservation. Social comparisons, you save 20% more than your neighbors, motivate change. Community programs. Local initiatives, such as car sharing, urban gardening, and green volunteer projects, foster participation and habit formation. Policy-driven behavior change. Regulations like mandatory recycling, building energy codes, or congestion charges influence behavior at scale. Social dynamics and adoption of sustainable practices. Peer influence and social norms. Behavior is influenced by neighbors, coworkers, and social networks. Community recognition programs reward positive behavior and create normative pressure. Equity considerations. Ensure that low-income and vulnerable populations can access and afford sustainable options. Avoid policies that disproportionately burden disadvantaged groups. Cultural context. Tailor interventions to local customs, habits, and social expectations. Role of technology in engagement and behavior change. Digital platforms. Apps, websites, and social media can educate, track, and incentivize sustainable behaviors. Smart meters and IoT devices. Provide occupants with actionable insights into energy, water, and waste performance. Gamification. Reward systems and challenges motivate communities to reduce consumption and participate in sustainability programs. Virtual participatory planning tools. Online simulations allow residents to visualize urban design scenarios and provide feedback. Case studies. Stockholm, Sweden, smart energy communities. Residents use energy dashboards and receive incentives for reducing electricity consumption. Community engagement led to measurable reductions in energy use and peak demand. Curitiba, Brazil, participatory urban planning. Citizens contributed to the development of transit-oriented neighborhoods and green spaces. Improved public transit adoption and local satisfaction with urban infrastructure. Melbourne, Australia, urban greening programs. Community-led tree planting and green roof initiatives increased local awareness, social cohesion, and urban resilience. Integrating community engagement with urban planning. Early engagement. Involve communities from the design stage to ensure projects meet local needs. Feedback loops. Collect, analyze, and respond to community feedback throughout implementation. Partnerships. Collaborate with NGOs, schools, and local businesses to amplify outreach and participation. Monitoring behavior change. Track participation rates, resource savings, and social outcomes to refine programs. Summary. Community engagement and behavior change are critical to the success of sustainable and resilient urban development. Engagement fosters ownership, equity, and practical implementation of climate adaptation and mitigation measures. Methods include participatory planning, public consultations, citizen science, and educational campaigns. Behavior change can be promoted through nudges, feedback, incentives, and policy interventions. Technology enhances engagement through dashboards, apps, gamification, and virtual planning tools. Case studies from Stockholm, Curitiba, and Melbourne demonstrate the effectiveness of participatory approaches. References for Chapter 13. United Nations 2016, Urban Residents as Change Agents for Sustainable Cities. C40 Cities 2019, Engaging Communities for Climate Action. Thaler R. and Sunstein C. 2008 Nudge, Improving Decisions About Health, Wealth, and Happiness. Week A. et al. 2011, Key Competencies in Sustainability, a reference framework for academic program design. Chapter 14, Technology and Innovation in Climate-Resilient Cities. Introduction. Climate-resilient cities leverage technology and innovation to reduce greenhouse gas emissions, enhance infrastructure durability, and improve urban livability. Smart systems, data analytics, renewable energy, and advanced materials enable cities to respond dynamically to climate challenges. This chapter explores emerging technologies, innovative urban solutions, and how digital transformation supports mitigation and adaptation in the built environment. Smart cities and digital infrastructure. Definition and scope. Smart cities use information and communication technologies, ICT, to optimize urban services, improve resource efficiency, and enhance resilience. Smart energy management. Smart grids enable two-way energy flow between producers and consumers. Integrates renewable energy, energy storage, and demand-side management for efficient energy use. Intelligent Transport Systems, ITS. Real-time traffic monitoring, route optimization, and adaptive signal control reduce congestion and emissions. Supports electric and shared mobility systems. Digital twin technology. Virtual models of cities simulate urban dynamics, infrastructure performance, and climate risks. Enables planners to test adaptation strategies before implementation. Renewable energy and decentralized systems. Distributed energy systems. Rooftop solar PV, wind turbines, and microgrids reduce dependence on centralized fossil fuel power. Energy storage innovations. Battery systems, thermal storage, and smart energy management balance supply and demand. Integration with smart grids. Enables predictive energy management, peak load reduction, and enhanced resilience during outages. Water and waste management technologies. Smart water networks. Sensors detect leaks, monitor quality and optimize distribution. Supports water conservation and reduces energy consumption. Stormwater management and flood monitoring. IoT-enabled sensors track rainfall and water levels, triggering early warning systems. Automated flood barriers and smart drainage reduce damage from extreme events. Circular waste management. Waste-to-energy systems, sensor-enabled bins, and automated sorting improve recycling rates. Supports resource efficiency and carbon reduction. Climate-resilient building technologies. High-performance building materials. Thermally efficient, low-carbon and durable materials reduce operational emissions. Automated energy systems. Building management systems, BMS and AI optimize heating, cooling, lighting, and ventilation. Adaptive facades and smart glazing. Dynamically respond to sunlight, temperature, and occupancy to improve energy efficiency. Green and blue infrastructure. Integration of green roofs, living walls, and water features enhances resilience and urban microclimates. Mobility and transportation innovations. Electric and hybrid vehicles. Reduce tailpipe emissions and support sustainable transport systems. Shared mobility platforms. Car sharing, bike sharing, and ride-hailing reduce private vehicle dependency. Autonomous vehicles and AI traffic management. Optimize traffic flow, reduce congestion, and lower emissions. Multimodal transport integration. Seamless coordination between public transit, cycling, walking, and electric vehicles. Data-driven urban resilience. Climate risk mapping. Geospatial data and predictive analytics identify vulnerable areas. Early warning systems. Sensors, AI, and communication networks alert residents and authorities to extreme weather events. Performance monitoring. Continuous monitoring of infrastructure and environmental conditions supports adaptive management. Open data platforms. Share urban energy and climate data to enable collaboration, innovation, and citizen engagement. Innovation in materials and construction. 3D printing and prefabrication. Reduces waste, energy use, and construction time. Self-healing concrete and smart materials. Enhance durability and reduce maintenance in climate-exposed structures. Biomimicry and nature-based solutions. Use natural systems for cooling, water management, and resilience. Case studies. Songdo, South Korea, Smart City. Fully integrated ICT infrastructure monitors energy, water, transport, and waste systems. Optimizes efficiency and improves resilience. Amsterdam Smart City, Netherlands. Uses digital twins, smart grids, and community engagement to reduce emissions and enhance urban sustainability. Masdar City, UAE. Combines renewable energy, low-carbon buildings, automated transport, and data-driven management for a climate-resilient urban model. Challenges and considerations. Data privacy and security. Smart city technologies require careful handling of personal and operational data. Cost and accessibility. High upfront investment may limit adoption in developing regions. Interoperability. Diverse systems and standards must be integrated for efficiency and resilience. Social acceptance. Technology adoption depends on public trust, awareness, and behavior change. Summary. Technology and innovation are key drivers of climate-resilient, low-carbon cities. Smart cities, IoT, digital twins, and data analytics optimize urban systems and improve decision-making. Renewable energy, energy storage, and decentralized systems reduce emissions and enhance resilience. Advanced materials, adaptive buildings, and green infrastructure support mitigation and adaptation. Mobility innovations, autonomous systems, and multimodal integration reduce transport emissions. Case studies demonstrate the practical application and benefits of technology-enabled resilience. Challenges include cost, interoperability, data privacy, and social acceptance. References for Chapter 14. Batty M. et al. 2012, Smart Cities of the Future. International Energy Agency, IEA, 2021, Digitalization and Energy Efficiency in Cities. C40 Cities 2020, Technology for Urban Climate Action. Albino V. Berardi U. and D'Angelico RM 2015, Smart Cities, Definitions, Dimensions, and Performance. Chapter 15, Future Trends and the Path to Net Zero Cities. Introduction. The concept of net zero cities, urban areas that balance carbon emissions with removal through technology, green infrastructure, and sustainable practices, is increasingly central to climate action. Achieving this goal requires integrating mitigation, adaptation, innovation, and community engagement across all sectors of the built environment. This chapter examines emerging trends, technological innovations, policy directions, and integrated strategies shaping the future of climate-resilient cities. The Net Zero City Concept. Definition. A city that achieves net zero greenhouse gas emissions across its operations, buildings, transport, and infrastructure. Incorporates renewable energy, carbon-neutral construction, efficient mobility, and green spaces. Core principles. Energy efficiency, minimizing energy demand across buildings, transport, and industry. Renewable energy integration, generating clean energy locally and through grid connections. Carbon offsetting and sequestration, urban forestry, green roofs, and carbon capture systems. Resilience, ensuring climate adaptation measures are embedded in planning. Emerging urban planning and design trends. Compact and mixed-use urban forms. Reduce transport-related emissions, promote walkability, and enhance land use efficiency. Transit-oriented development, TOD. Integrates high-density development with public transport hubs to minimize reliance on private vehicles. Green and blue infrastructure networks. Urban forests, parks, wetlands, and waterways mitigate heat, improve stormwater management, and sequester carbon. Climate adaptive zoning. Anticipates sea level rise, flood risk, and heat stress to guide development in low-risk areas. Integration of advanced technologies. IoT and smart cities. Sensors, data analytics, and predictive algorithms optimize energy, water, and mobility systems. Digital twins and simulation models. Virtual city models test climate interventions, building designs, and infrastructure scenarios. AI and predictive urban management. AI forecasts energy demand, traffic patterns, and climate hazards for proactive planning. Distributed renewable energy systems. Rooftop PV, urban wind, and microgrids enable decentralized energy production and resilience. Low carbon and circular construction practices. Mass timber and sustainable materials. Store carbon in buildings while reducing reliance on energy-intensive concrete and steel. Modular and prefabricated construction. Reduces material waste, construction time, and embodied carbon. Life cycle carbon accounting. Comprehensive evaluation of embodied and operational carbon ensures sustainability throughout the building life cycle. Adaptive reuse of existing buildings. Minimizes demolition waste and reduces energy expenditure associated with new construction. Energy, transport, and mobility innovations. Electrification of transport. EV adoption, charging infrastructure, and electrified public transit reduce urban emissions. Mobility as a Service, MaaS. Integrates shared electric and public transport options to reduce private vehicle dependence. Active transport infrastructure. Bike lanes, pedestrian streets, and urban trails promote low-carbon mobility. Smart traffic and congestion management. AI and sensors reduce congestion, emissions, and fuel consumption. Urban resilience and climate adaptation. Flood and heat mitigation. Green roofs, permeable surfaces, urban forests, and reflective materials mitigate extreme weather impacts. Disaster-resilient infrastructure. Buildings, transport networks, and utilities designed to withstand storms, floods, and heat waves. Community-based resilience. Engaging local populations in adaptation planning enhances preparedness and equitable outcomes. Ecosystem-based solutions. Restoring wetlands, mangroves, and urban green corridors reduces disaster risks and supports biodiversity. Policy and governance for net zero cities. Integrated urban climate policies. Combine mitigation, adaptation, and sustainability into a unified urban planning framework. Financial incentives and green investment. Green bonds, carbon pricing, and low-interest financing support sustainable infrastructure projects. Performance-based building codes. Encourage or mandate energy efficiency, renewable integration, and climate resilience. Data-driven governance. Monitoring, evaluation, and reporting inform policy adjustments and community engagement. Community engagement and behavior change. Participatory planning. Residents co-create solutions for mobility, energy, and green infrastructure. Behavioral incentives. Nudges, gamification, and real-time feedback encourage energy and water conservation. Education and awareness. Schools, media, and community programs build a culture of sustainability and resilience. Global case studies of net zero or low-carbon cities. Copenhagen, Denmark. Ambition to become carbon neutral by 2025 through renewable energy, cycling infrastructure, and district heating. Vancouver, Canada. Targets net zero energy buildings, electric mobility, and extensive green infrastructure. Freiburg, Germany. Integrated solar energy, low-carbon construction, public transit, and participatory planning for sustainable urban living. Challenges and opportunities. Integration across sectors. Aligning energy, transport, water, and waste management requires strong coordination. Financing and investment gaps. High upfront costs can limit adoption, requiring innovative public-private partnerships. Technological equity. Ensuring access to smart systems and low-carbon technologies for all populations. Behavioral and cultural shifts. Achieving net zero cities depends on widespread adoption of sustainable practices by residents and businesses. Opportunities for innovation. Advances in AI, IoT, renewable energy, low-carbon materials, and circular economy strategies accelerate progress toward net zero. Summary. Net zero cities balance greenhouse gas emissions with removals while maintaining resilience and livability. Achieving this goal requires integrated approaches spanning urban planning, building design, transport, energy, and infrastructure. Advanced technologies, smart systems, AI, IoT, digital twins, enhance decision-making efficiency and resilience. Low-carbon and circular construction practices reduce embodied and operational emissions. Community engagement, behavior change, and policy frameworks ensure inclusive, effective, and sustainable outcomes. Global case studies demonstrate successful pathways, though challenges remain in integration, financing, equity, and cultural adoption. Emerging trends suggest that net zero, climate-resilient cities are achievable through coordinated innovation, governance, and citizen participation. References for Chapter 15. See 40 Cities 2020, Net Zero Cities, Global Outlook and Strategies. United Nations Environment Programme, UNEP, 2021, Pathways to Sustainable Urban Development. International Energy Agency, IEA, 2021, Net Zero by 2050, Cities Sector Report. Romero-Lancao P. 2016, Urban Sustainability and Resilience, Pathways to Net Zero Cities. Chapter 16, Conclusion and Recommendations. Introduction. Climate change presents unprecedented challenges to cities and the built environment. Rising temperatures, extreme weather, sea level rise, and resource constraints demand urgent and coordinated action. This book has examined the intersection of climate science, urban planning, building design, policy, technology, finance, and community engagement. Chapter 16 synthesizes the lessons learned and provides practical recommendations for policymakers, architects, urban planners, developers, and citizens aiming to create low-carbon, resilient, and sustainable urban environments. Key insights from the book. Climate change and urban vulnerability. Cities are major contributors to greenhouse gas emissions and are highly exposed to climate risks. Urban systems, including buildings, transport, and infrastructure, must be adapted to withstand extreme weather events. Mitigation strategies. Energy efficiency, renewable energy integration, low-carbon materials, retrofitting, and sustainable urban planning are central to reducing emissions. Life cycle carbon assessment and carbon accounting ensure that interventions achieve measurable outcomes. Adaptation and resilience. Green and blue infrastructure, climate-resilient building design, disaster preparedness, and ecosystem-based solutions enhance urban resilience. Risk-informed planning and hazard mapping are essential to minimize losses and protect vulnerable populations. Policy, governance, and finance. Robust regulatory frameworks, building codes, incentives, and financing mechanisms enable sustainable urban development. Public-private partnerships, blended finance, and green bonds unlock investments for climate-resilient infrastructure. Technology and innovation. Smart cities, digital twins, IoT, AI, and predictive analytics optimize urban systems for efficiency, resilience, and sustainability. Advanced construction techniques, adaptive buildings, and low-carbon materials reduce embodied and operational emissions. Community engagement and behavior change. Engaging residents, businesses, and local stakeholders fosters ownership, compliance, and adoption of sustainable behaviors. Education, nudges, gamification, and participatory planning are critical to shaping resilient and low-carbon urban communities. Future trends and net zero cities. Achieving net zero urban environments requires integrated approaches across energy, transport, buildings, and infrastructure. Emerging technologies, circular economy practices, and ecosystem-based adaptation create opportunities for fully sustainable cities. Recommendations for stakeholders. Policymakers and urban planners. Integrate climate considerations into urban planning. Incorporate mitigation and adaptation strategies at all stages of urban development. Enforce and update building codes. Ensure energy efficiency, resilience, and low-carbon construction practices are mandatory. Promote inclusive governance. Engage marginalized communities in decision-making and ensure equitable access to sustainable infrastructure. Architects, engineers, and developers. Adopt low-carbon design practices. Use sustainable materials, passive design strategies, and renewable energy integration. Prioritize retrofitting and adaptive reuse. Upgrade existing building stock to enhance energy efficiency and resilience. Leverage technology. Employ smart systems, digital twins, and predictive modeling to optimize performance. Financial institutions and investors. Support climate-resilient investments. Use green bonds, blended finance, and impact investment to fund sustainable projects. Incentivize energy efficiency and renewable integration. Provide low-interest loans, grants, or tax benefits for sustainable building practices. Promote transparency and reporting. Encourage projects to measure, verify and report emissions reductions and resilience outcomes. Communities and residents. Participate in local sustainability initiatives. Engage in urban planning, green infrastructure programs, and community-based resilience projects. Adopt low-carbon behaviors. Reduce energy and water consumption, recycle and prioritize low-emission transport options. Support policy and innovation. Encourage local governments and businesses to implement sustainable and climate-resilient solutions. Path forward for climate-resilient cities. Holistic and integrated approach. Combine mitigation, adaptation, technology, governance, finance, and behavior change into unified strategies. Data-driven decision-making. Continuous monitoring, evaluation, and reporting inform evidence-based policies and interventions. Scaling innovation. Share successful models, replicate low-carbon construction techniques, and integrate smart city technologies. International collaboration. Exchange knowledge, technical expertise, and financing mechanisms to accelerate global climate action. Equity and inclusion. Ensure all populations benefit from climate-resilient and sustainable urban development. Concluding remarks. The built environment is both a major contributor to climate change and a critical arena for solutions. By integrating science, technology, policy, finance, and community engagement, cities can transform into low-carbon, resilient, and livable spaces. Achieving climate-resilient, net-zero cities is not merely a technical challenge, it is a societal opportunity. Through innovation, collaboration, and sustained commitment, urban areas can become powerful agents for climate mitigation and adaptation, securing a sustainable future for generations to come. References for Chapter 16. United Nations 2019, World Urbanization Prospects, the 2018 revision. C40 Cities 2020, Net Zero Cities, Global Strategies for Sustainable Urbanization. Intergovernmental Panel on Climate Change, IPCC, 2022, Climate Change 2022, Mitigation of Climate Change. World Bank 2020, Sustainable Cities, Climate Action and Resilience Strategies.